Hello, everybody. So last video, we completed proving the closure properties for regular languages. And today we're kind of doing the counterpositive, or we're showing that these closure properties are not just some arbitrary closure properties, but in fact, they completely characterize, okay, starting over. Hello, everybody. So last time we've completed proving the closure properties for regular languages. And today what we're going to show is that regular languages are completely characterized by these closure properties, that in fact you can define regular languages through these closure properties. And we'll do this through a notion called regular expressions. And this picture is the most regular expression I could find on the web. So, regular expressions are going to define languages through these properties, closure properties, so through some logical operations. It's a different way of viewing computation. So computation here is going to be a simple logical description of the language. And in fact, we're going to see that this very different way of viewing computation are going to boil down to a computational model that we already know and like. So we're going to ask, what is the complexity of describing the strings in the language? So let's jump into the definition of regular expression, and this is going to be an inductive definition. So sigma is an alphabet. We define the regular expressions over sigma inductively. For every alphabet in character sigma in sigma, sigma is a regular expression. Epsilon is also a regular expression. The empty set is also a regular expression. We'll talk about what each one is corresponds to. And so these are the basic of the induction. So the basic regular expressions are going to be any sigma, epsilon, and the empty set. Now we're going to define things recursively. If R1 and R2 are both regular expressions, then R1 concatenated with R2 is a regular expression, which we denote like multiplication. R1 plus R2 is a regular expression, and R1 star is a regular expression. So by now we defined all the regular expressions in the world over sigma. We still didn't say what are these regular expressions, what's the, so we defined the syntax of regular expressions, but not their semantics. Let's say that because we're defining through operations, we need to define the precedence order of these operations. It will be very similar to what we think in algebra when we interpret star as exponentiation. So it's first exponentiation, then product, then addition. And of course, you can break this order and give priority by using parentheses. So example, R1 star, R2 plus R3 equals first R1 star, then the product of that with R2, then adding R3. So now we want to say, what are these regular expressions? How do they represent languages? And we'll do it recursively. So for the base case, the regular expression sigma represent a language that contains a single word, and this single word contains a single alphabet character, sigma. The regular expression epsilon represents the language that only contains epsilon, only contains the empty string. And the regular expression empty set represent the empty set. And this is extremely confusing. It's so confusing that I remember being confused about it myself when I was an undergrad, and believe me, this was a while ago. And so what confuses is that these two things seem like they're almost the same, but they're very different. So this language is the empty set. So it's a language that contains no string, and in particular, it doesn't contain the empty string. This language is not empty. It contains a single string, and this is the empty string. So the empty string is different than the empty language. Now we need to define what do more sophisticated, more complicated regular expressions satisfy, and we add several operations, 3 operations, and we'll go one by one and say, what do they represent? So if R1 and R2 are the regular expressions that represent the languages L1 and L2, then R1 times R2 represent the concatenation of L1 and L2. R1 plus R2 represent their union, and R1 star represent L1 star. Recall that these are all operations that we discussed in the closure properties. So regular languages are closed under this, under these operations. So regular expressions represent languages. For every regular expression R, we will define L of R to be the language that R represents. So we talked before about L of a machine, and now we are going to refer to L of an expression. A string W in sigma is accepted by R or matches R if W is in the language that, that R represents. So we are kind of adopting the language of computation for these regular expressions, although they are not exactly computations, right? They are ways of describing languages. So let's look at some examples. 0, 0, 1, 0, 0, 1, 0, 1, 0, all match the expression 0, 1 in parentheses star 0. So this expression says that you can take 0, 1 any number of times, so either 0 times, 1 time, or concatenate it any k number of times, and then at the end you need to concatenate 0. So all of these match 0, 1 star 0. The string 1, 1, 0, 1, 0, 1, 1, 1, 0, 1, 0, 0, 1, 0, 1 matches 0 plus 1 star 0. In fact, every string that ends with a 0 will match this expression, because 0 plus 1 star matches the complete language. So assume that sigma is 0, 1. So we'll take the binary alphabet. What is a regular expression that matches the language W, such that W has exactly a single 1? And you can freeze me. This is 0 star, 1, 0 star. So this language are strings that has some zeros in the beginning. It can be 0 to any number of zeros in the beginning, then 1, and then any number of zeros at the end. How about the language W, where W contains 0, 0, 1, which should be reminiscent because we described the DFA for this language. So this is similarly 0 plus 1 star, so any string, concatenated with 0, 0, 1, concatenated with any other string, 0 plus 1 star. So what language does the regular expression empty set star represent? Slightly tricky, but this represents the language that contains only the empty string. Because as we said, the empty string is part of any language star. Because it means that you can take strings that are a concatenation of 0 or more elements of the language. How about W has length at least 3, and its third symbol is 0. So we now don't have star at the beginning. We have 0 plus 1. Any first symbol concatenated by 0 plus 1. Any second symbol. This third symbol being 0, and the rest is arbitrary. How about every odd position in W is 1? So the first is 1, and then it's 0 plus 1. So this is a string of length 2 that starts with 1. You can have it any number of times, a string in this family. So this will give you all the even strings, but you can also take it 0 times, and you concatenate it with 1 plus epsilon. So this will give us the empty string, which is in the language, because in the empty string there is no element in the odd position, and therefore it satisfies this requirement trivially. And the string that is just composed of a single alphabet character, which is 1. How about W? It has equal number of occurrences of 0, 1, and 1, 0. This sounds harder, right? You need to do some counting, which sounds like something that you cannot do. And in fact, in the next videos, we are going to show that these kind of regular expressions and DFAs cannot count. So here we're going to realize that this language that kind of is defined by counting has a different representation that that's much easier to understand, that's much easier to calculate. So what strings start with have the same occurrences of 0, 1, and 1, 0? First, these are strings of length less than at most 1. Because strings of length at most 1 has 0 occurrences of 0, 1 and 0 occurrences of 1, 0. So it's W equals 1, W equals 0, or W is empty. For the rest, it turns out that all you need to check is that W starts with a 0 and ends with a 0, or starts with a 1 and ends with a 1. So you get that you can show that then you have the same number of 0, 1s and 1, 0s. And the reason is that it doesn't matter how many times you have a 0. In parallel, it doesn't contribute not to the 0, 1s or to the 1, 0s. The only thing that matters is how many times you move from 0 to 1 and how many times you move from 1 to 0. And if you start with the same character as you end, you see that you move from 0, 1 to 1 the same number of times as you move from 1 to 0. Now, this representation is much easier to have with the regular expression. It's not a beautiful or nice or simple regular expression, but it's definitely doable. Right. So this is the claim. The claim is that a string W that has equal number of occurrences of 0, 1, and 1, 0 start and ends with the same bit. And again, this is not hard to prove. The regular expression gives you the three special strings, 1 plus 0 plus epsilon, plus all the strings that start and end with the 0, and all the strings that start and end with the 1. And in the middle, they can have an arbitrary string. So what we want to show, and we will partially show in the rest of the video, is that this new method of defining languages by regular expressions actually gives us a family of languages that we already know, the only family of languages we already know, and these are the regular languages. In other words, DFAs, NFAs, and regular expressions can represent the same family of languages. So L can be represented by some regular expression, even only if L is regular. This again will have two sides, and here we'll do the easier side and the hint on the more complicated side. It's a bit evolved, it's not hard, and you can read it in Sipser. So let's show the easier one, that L can be represented by some regular expression. It means that L is regular. So given any regular expression R, we want to construct an NFA N such that N accepts exactly the strings that are accepted by R. And the proof is going to be by induction on the length of the regular expression R. So the base case are regular expressions of length 1 exactly, and these are only the base cases of defining regular expressions. So it can be one that correspond to an alphabet symbol, one that corresponds to an empty string, and one that corresponds to the empty set. Each one of them has an NFA. So this is a non-deterministic finite automata that only accept the symbol sigma. This is a start vertex. You can only take a step with sigma and reach an accept state, and nothing else as a corresponding path. For accepting the empty string, we have this NFA, and the only thing that it accepts is the empty string. The moment you need to read any alphabet symbol, you have no transitions, and therefore you cannot accept it. And the empty string is something we already discussed in the past. So it's this NFA that has a single state which is rejecting, and you cannot accept anything with a single state that is rejecting. Now we want to do the induction step. The induction step assumes that for every regular expression of length at most k represents some regular language. Means that it has some DFA that recognize the same language. So consider a regular expression of length k larger than 1. These kind of regular expressions are not the base regular expressions. They are obtained by one of the three operations. And therefore, we will look at the three operations, get shorter regular expressions, and use the induction step for them. So there are three possibilities for R. It can be R1 plus R2, R1 times R2, R1 star. every regular expression that's larger than, its length is larger than 1 as one of these forms. Now, by induction for the R1 plus R2, R1 and R2 represent some regular language, L1 and L2. The language that R represent is the union of L1 and L2, and therefore L of R is also regular just by the union theorem. So here we're using the closure properties of regular languages. And the same holds for the two other operations. So if you look at R1 times R2, it corresponds to the language L1 times L2, to the concatenation of L1 and L2. And this is regular by the concatenation theorem. And finally, and when you look at the star, then L of R is the language that corresponds to L1. It's L1 star. And it's also regular by the star theorem. So because of all the closure properties we proved in the last videos, we get that any regular expression can only represent regular, any regular expression represent only regular languages. The other more interesting part is to, so if L represented by a regular expression, it is regular. The other one is to show that any regular language can be represented by a regular expression. And this will show that regular languages can be defined by their closure properties. Given an NFA that accepts the language represented okay, so this is an example, sorry. Give an NFA that accepts the language represented by this regular expression. And we can do it. So the proof that we said that any regular expression is accepted by some NFA was actually a constructive proof. So we start by having this NFA for 1. So this is the first regular expression with it we have. We are concatenating it with an NFA that accepts either 0 or 1. So by now the regular expression is 1 times 0 plus 1. And now we need to apply the star operation, and we know how to represent the star with an NFA. This was the construction that we used to prove the star. So we looked at the accept state, connected it to the start state, and added this additional start state. So now this gives us a regular expression. I mean, this NFA corresponds to the languages accepted by this regular expression. So this is a kind of exercise you may be asked to do, taking a regular expression and turning it into an NFA. Now let's talk about the other side, and I'll hint on it, and you can see it in CIPSR. That if L can be, so if L is a regular language, then there is a regular expression for it. And the idea is to transform an NFA for L into a regular expression. And the way we'll do it is by removing states and relabeling the edges, the arcs, with regular expressions. And by the time we remove everything, we'll get the regular expression we want. So this requires us to talk about something that is not exactly an NFA. In the process, we're going to have something where the edges are labeled not by letters, not by a single alphabet letter, but by an entire regular expression. So it will be able to read an entire substring and move from one to the other based on the regular expression. This gives us this generalized NFA that the book refers to as GNFA. This is very similar to how we got to NFAs, right? With a proof, within the proof, we started with the DFA, we reversed it, we got this NFA. And what we did was to say, okay, this NFA is actually a creature we can study and understand and use, and that's how we complete it. So here in the process, we get something that's stronger or more general than an NFA, and that's the byproduct of the proof, is that it kind of gave us this new object. And as I said, I'm not going to actually prove everything, but I'm going to give you an example. So this is a generalized NFA. This is still, you have still the start vertex, you still have accept vertices, but now the edges are labeled by regular expressions. This one is by A star B, this by CB, this by A. And now when you take a path, each edge can read not a single symbol, but any string that corresponds to the regular expression. So as an example, is this string accepted or rejected by this generalized NFA? Is this string accepted or rejected? So let's look at the first one. The first one, you have 3 A's, right? Which correspond to A star and a B. So you can read B and move from Q0 to Q1. Then you can read CB twice and reach here, and read A and reach here. So this is accepted. How about BBA? BBA, B is still accepted by this. A star B matches the string composed only of B. Then B, then you need to take a B, but you don't have a B anymore. You can have a CB here and an A here. So this is rejected. There is no path from start to end that accept that. Is BCB A accepted or rejected? This is accepted because you can take B here, then CB here, and then A. This GNFA recognizes the language that corresponds to the regular expression that starts with A star B, concatenated with CB star, because you can take this edge 0 or any number of times, concatenated with A, because at the end you need to take A to reach here. So this is a generalized NFA, which corresponds to a regular expression. So let's give a hint of the proof. You start with an NFA. You add a unique start and accept states. And the idea is that over time, we're going to get rid of everything in between, all the original NFA, and we'll stay with a single edge from start to end. And this single edge will have as its label the regular language that that corresponds to the the regular expression that corresponds to the language accepted by this NFA. So while the machine has more than these two states, you pick an internal state, you rip it out, and you relabel the arrows that go through it with regular expressions. And so for every path of length 2 that goes through this state, you're going to have a regular expression. So let's look at just at this example where you have 0, 1, 0. The only state that we can rip off is this one. And the regular expression that we need to replace it is 0, 1, star 0. So there was a path of length 2 going through this vertex that we just removed, and we replace it with an edge. This particular path we replace with an edge, and we'll do it for every path that goes through this node that we're going to remove. So more generally, once you already have edges that are labeled by regular expressions, you're going to remove an internal edge, and you're going to replace every path that goes from Q1 to Q3 that could have gone by this edge, and in addition, the path that didn't go through this vertex. So this will be replaced by this regular expression and this regular expression times this regular expression star times this regular expression. So it's just that. So R that goes from Q1 to Q2, and then R that's all the regular expression that stay put, star, and the one from Q2 to Q3, plus the one that went directly. And we'll do it for every two remaining vertices. So let's do it just by an example. If this is the NFA we start with, we need to remove two internal vertices. Let's remove this one. Let's see it again. To remove this one, it's an empty string, anytime, any number of A's, and then B. So this is just A star B. And now we need to remove this one. So it's this regular expression concatenated with this regular expression star, concatenated with this one, which is empty. This is A star B times A plus B star times the empty string, which we don't need in the regular expression. So that was an example of how you do the other direction. You can see more details in CIPSR, and whenever we'll use it, if at all, we'll use it with a very simple example, so it won't be very challenging. Right. So this just the conclusion. The regular expression that we have here is just the remaining edge. So what have we seen? We've seen throughout this bunch of videos, we have a very interesting picture of what can be done by DFAs. So DFAs give us our equivalent to regular languages. This is just by definition. We define regular languages to be ones that are accepted by DFAs. DFAs can be done by NFA just because this is a generalization, but we've shown the other direction that's more interesting. NFAs can be reduced by to DFAs. So these two are equivalent as well. And we've seen that regular expressions are equivalent to NFAs. They accept the same family of languages. So essentially, all of these are equivalent. These are equivalent ways of understanding regular languages. You understand them as the languages recognized by DFAs, by NFAs, or represented by regular expressions. In conclusion, regular languages can be defined by their closure properties, and this is what we saw today. And this completed the picture and gave us a very nice understanding of what are regular languages. And in following with videos, we're going to look at what regular languages cannot do. So what's the limitation of regular languages? Thank you.